Hello, topic of this presentation is processing of exposure results composite material with the choice of their optimal composition. Problem. At the present stage of studying concretes, and composite materials in general, much attention is paid to their optimization, the study of their characteristics, the dependence of various properties on operating conditions. In particular, an important task is to determine the composition of composites, the characteristics of which are most resistant to operational impacts. First of all, it's the hardness of material, then the modulus of elasticity of the corresponding character. The problem statement consists in the optimal choice of those compositions of composite materials, in which their properties, hardness, modulus of deformation, and equilibrium modulus of elasticity change at least during the exposure time. The materials were rated under the influence of positive and negative temperatures, and under the influence of high humidity and variable temperatures. Thermocyclic tests of samples, composites, were carried out in laboratory conditions in the climate chamber of VIAM, All Russian Research Institute of Aviation Materials, in two stages. At the first stage, a batch of samples was tested with 15 thermocycles, and at the next stage, the second batch of samples was tested with 13 thermocycles. One 20-hour thermal cycle includes 4 thermal states. Tests of samples under cyclic influence of positive and negative temperatures included the following operations: cooling of samples from room temperature plus 23 degrees of Celsius to minus 50 degrees of Celsius, about an hour 50-55 minutes. Exposure of samples at a temperature of minus 50 degrees of Celsius, 9 hours. Natural heating of samples to room temperature plus 23 degrees of Celsius with the camera of at least 5 hours. Exposure of samples at room temperature plus 23 degrees of Celsius, 9 hours. Test of samples at high humidity, 98%, and varying positive temperatures included other parameters. Heating of samples from room temperature plus 23 degrees of Celsius to plus 60 degrees of Celsius, about 5 minutes. Exposure of samples at a temperature of plus 60 degrees of Celsius, 9 hours. Natural cooling of samples to room temperature plus 23 degrees of Celsius with a camera of at least 5 hours. Exposure of samples at room temperature plus 23 degrees of Celsius, 9 hours. As can be seen from the tables 1 and 2, the properties of the compositions change relative to their control values during the exposure time. Their relative changes are of interest. In this regard, the values of the tables should be converted to relative values, relative to the control values, relative to the values in the row with the indication 0. 0 is the duration of the test. This will allow you to compare the properties of materials with different ranges of changes in a particular property. These two selves may differ by several orders of magnitude. For an explanation, see Table 3, which summarizes the relative values for the first two compounds A1 and A2 from Table 2. Regardless of the purpose of a particular composite, the natural requirement is primarily the immutability of its properties. In this case, the relative values of the properties will be equal to 1. At the same time, the actual state of things may not meet the requirement, that the property indicators remain unchanged during the exposure time under the specified operating conditions. For comparison of the desired requirement of immutability of properties of their actual changes in Figure 1, Figure 2, charts are presented in relative units. On the Figure 1 you can see a property is invariant for the tests. On Figure 2 you can see the property depends on the test. As shown in the tables 1 and 2, relative change in properties may exceed the level of the control sample property during the test. In this regard, it's proposed to calculate the area under the polyline curve, Figure 3 and 4, and compare it with the area of the rectangle S-rect with the height equal to 1. In the case of Figure 1, S-rect is equal to 45 square units. On the Figure 3 you can see monotonous decrease of the property value. On the Figure 4 you can see non-monotonic change in the values of the properties. Here we propose an addition to the criteria for searching for the optimal composition of a number of composites that have been tested under test operation conditions. For the first S criterion, we used the S polygon, S-rect area ratio. For Figure 5 and 6 show the construction to determine the criteria key high I is equal to 1, 2 and 3. On Figure 5 you can see to determine the high criterion. On Figure 6 you can see to determine the key I criterion. The criterion S, which take into account the error ratio, is formed in the form CI is equal to the S polygon and S-rect. Another criterion, the G criterion, is defined as a sum of the specified criteria. G is equal to C plus Ki plus Hi. I is equal to 1, 2, 3, 4. Experimental result. Taking into account the fact that the selected criteria should be minimized, then the formation of estimates for the criteria will be arranged in descending order. The size of the matrix of possible criteria values should be assumed to be greater than the number of alternatives, the number of compositions. This will allow you to divide the estimates in a wider range, which in turn will almost eliminate the coincidence of the sum of estimates for alternatives. In the conducted experiments, the size of the matrix with estimates is assumed to be equal to twice the size of the number of alternatives. Table 4 shows a matrix of estimates of composites exposed during cyclist temperature tests. Table 4, the final matrix of the evaluations for cyclic temperature testing. In Table 4, the alternatives are the teams ranked by total points. Experimental data are taken from Table 1. As can be seen, the optimal composition of the composite corresponds to A10, which more than the rest meets the conditions for optimal selection among a given number of samples that have been tested at a temperature change for 45 days. For visual control of the relative change in the hardness of the first group of composites, a diagram is shown in Figure 7, which shows that the performed ranking of samples, Table 4, is consistent with the nature of the change in the hardness of each composition's alternative during the test time. A similar table, Table 5, is provided by optimal selection of composites that have been maintained in conditions of high humidity and positive temperatures. On Table 5 you can see final rating matrix for composite exposure in conditions of high humidity and positive temperatures. According to the results of Table 5, we conclude that the most preferred composite is A1 when tested in conditions of high humidity and positive temperatures. Conclusions. A method for solving a multi-criteria, multi-dimensional optimization problem is proposed, which allows it to be applied fairly quickly in experimental studies to determine the optimal composition of a number of studies composites. The criteria for searching for the optimal compositions of composites that have passed tests with the measurement of free properties of composites are determined. It was stated that the number of properties can be arbitrary. The number of exposure points can also be arbitrary. The method is focused on the use of programming tools in high-level languages. At the same time, the authors are aware that the results obtained are limited to the time period of the tests. This means that extrapolating results may not match experimental results obtained over a longer period of time. Thanks for your attention.